Rebecca from Squirrels, and I'm here to introduce you to the YouTube live streaming feature in Reflector 2. Live streaming video is
Hey, Jacob. Yeah, I can go through the first one. I think you're overthinking it. It really isn't that tricky. So we'll just go through the very first one. I'll try and, I was trying something new. Oh, farts. Well, anyways, I thought that was going to work, but it didn't. The TV just unplugged. So if you go to the worksheet, so the first one, a ball rolls down a slope and is launched horizontally. So all it's saying is that it's going down a ramp. And so all you're doing is you're comparing EP. So if it's on the top of a 27, what is it again? 29 centimeter height. So you'll have the EP at the top, which is just MGH, and then it's going to convert down into EK. And remember from grade 11, so it doesn't give you the mass. So remember that the mass is going to cancel out. So you have EP at the top equals MGH because there's no energy destroyed or created. So those M's are going to cancel. And so you're just going to end up with GH equals 1/2 V squared. And then with that, you can solve for the final speed of the ball right before it hits the ground. And then what the question is asking you to do is use horizontal projectile motion where VI and the Y is equal to 0. And you can calculate VF right before it hits the ground because your delta D equals VIT plus 1/2 AT squared. And then so once you cancel out that VIT because it's 0 and it's launched horizontally, you're just going to end up with delta D equals 1/2 AT squared where A is G. And then once you have that, you're going to compare those two speeds and they should be very similar but not the same because of the rotational energy. Megan, you asked to go over the second question. Did that help, Jacob, or was that too fast? Oh, okay, cool. So Megan, you're stuck on 2B or not 2B? No. So this one, a Lego car is released on a ramp 1.4 meter above the floor, then rolls along the floor. Oh, okay. So this was, I think, supposed to be a bit of a lab that we did in class. I just took this off stuff that we did last year. So you could measure how far that it went. But so just skip that one because you're not going to know the motion along the floor. Or if you want to do the lab at home, just take a book and put it up and then run it, but I wouldn't do that. For the third question, a mass is attached to a spring scale and a long string to form a simple pendulum. The mass is rated 30 and then down, how fast? So this is the same thing. You don't have a scale at home. But at the bottom, the scale should just read FG, right? Because of the vectors. 5 was a bit weird. Oh, this is fun, actually. So a vacuum cannon, just like a potato launcher, or remember we watched that thing with the golf ball in class? So the air will do work on the ball in the amount of P equals pi r squared L. So this is just hypothetical, right? So you know that the pressure is P, so 10 kilopascals. Pi obviously is pi. And then the radius is going to be the radius of the actual launcher and then the length. So if you had a vacuum cannon that was one meter long, basically all I want you to do is make some measurements with variables to find the muzzle velocity, right? So in this one, you know that work is equal to the object's change in energy, in this case, a potato or a ball going down the vacuum cannon. And so the work done is equal to that formula P pi r squared L. And so you're going to say the initial work is equal to the change in energy. So it's going to be, let's just call it EP. Oh no, EA for air pressure energy. And so all of that air pressure energy is going to be converted into kinetic energy. So the work done on the ball over that length, obviously if it's in there longer, it's going to shoot faster. If it's in there under more pressure, it's going to move faster. So your equation is going to end up being the EK, or kinetic energy, which is just your muzzle velocity, equals 1/2 mv squared, is equal to P pi r squared L. And then so you just rearrange 1/2 mv squared. So v squared equals 2 L, 2p pi squared L over, yeah, I would just leave it as L, Jacob. L and R. So just leave it as the variables. So you're just going to end up with V equals the square root of 2, whatever that formula that I can't remember right now. Question 3, Meg. Yes. Is that good, Jacob? Yeah, that's good. Okay. So question 3, Megan, it's going to be on a spring scale. And so the spring scale essentially is just hanging and making a pendulum. And so if you raise the pendulum up 30 degrees, you're gaining height, or h, right? And so just use that variable h Or does it tell you how long the string is? No. Okay, so yeah, you're just going to have to keep it in variable form. So the mass is attached to a spring scale, so that mass M, and the long string L, so it's going to be raised a certain height, H. And so mgh here is going to equal 1/2 mv squared. And the scale at the bottom, because they're just like here, is just going to read Fg. So really, it's just like a swing problem last year. Question 6, Jacob. So in this one, Canon uses compressed air. You're going to use that same formula. So your efficiency is 35% efficient. So you're going to use that same pumpkin, that same thing that was talked about in that earlier question, where the work done on the pumpkin, the sled one. After bobsled race, the sled and the riders are slowed down by a section of track inclined at 30%. What is the with the coefficient of friction of that? The sled is moving there at the bottom. How far does it travel along the incline before stopping? Okay. So Jacob, for this one, you're not going to need the mass, I don't think, if that's what you're worried about. So what I would do is, if you know that you first know, it seems to be labeled as 7 on the answer. Okay. All I would do is you have EK 1/2 mv squared at the bottom of the incline. And so as you move up the incline at 30 degrees, the work done is going to be equal to mgh plus force times distance of friction. So what you need to do is calculate If you know it's going at 35 meters per second at the bottom, you're going to find the kinetic energy at the bottom, and that is going to be converted into mgh, and you're solving for h of the hill, and then you're going to need to find the frictional force, and that times d, and then you're going to have to solve for that same distance horizontally. You're going to need to use trig for the mgh part. That's a hint. Right, so you're solving for the displacement going up the hill, but you don't know how far. The question is asking for the length that it's on the hill, and you don't know the length nor the height. So you're going to have to use a trig ratio somewhere in there. Megan, we can't go over the test yet. There's still 3 or 4 people that haven't completed it yet. I'm not really sure how I'm going to do that moving forward because the timelines are kind of tricky. I'll send you an email with the solutions after the due date is done. But again, I need to give people the opportunity to do the tests. But we'll figure something out. I know you want to know the answer. One last thing, the same question for work. Would we make work equals for yes equals to the friction force and FGI? Yes. Yes. So your F net is going to be the sum of FGI pushing down and the frictional force being done on it. I wonder if you even need the MGH in it, if you can just do it with work. Because the MGH is kind of accounted for going up the hill. Megan, for the dynamics unit or the energy unit? I can give you some more energy ones if you want a more of a refresher. I think the textbook ones are easier than just jumping right into this trickier stuff. Yeah, I can give you some more energy questions. I probably could have just typed it. That was dumb. Yes. Jacob, I would maybe try something like this for that sled question. Oh, it's flipped. No. Anyway, so in this one, the velocity at the bottom, which you know is 35. Oh, right, we're not solving for B. Anyways, we're solving for this right here, the D. I would try that one. This is not an ideal teaching format. I apologize. I'm sorry.